Crystal field theory is proposed by Hans Bethe and Van Vleck. VB theory helps us to visualize bonding in the complexes. However, it has some limitations. Hence, crystal field theory to explain some of the properties like color, magnetic behavior, etc. This was originally used to explain the nature of bonding in ionic crystal. Crystal field theory was used to explain the bonding in ionic crystal. Later on, it is used to explain the properties of transition metals and their complexes. Let us study some of the assumptions in the crystal field theory. The first one is crystal field theory assumes the bond between the metal and ligand is purely ionic. The bond between the metal and ligand is purely ionic. Usually, in ionic bond, the electrostatic force of attraction is existing. That is, the attraction between electron-rich ligand and the electron-deficient metal is called as what? Electrostatic force of attraction. Second assumption is in the coordination compounds, the central metal atom or ion and the ligands are considered as point charges. So the metal ion is a point charge and the ligand is another point charge. So a dipole is created in between this metal ion and the ligands. The electric dipole arises in between these two point charges. Based on these assumptions, the crystal field theory was formulated. Step 1. In an isolated gaseous state, all the 5 d orbitals of central metal ion are degenerated. So, degenerated means it is split into its sub-energy level and the ligands form a spherical field of negative charge around the metal ion. First, d orbitals in gaseous state, the metal ion is in gaseous state, it is degenerated into 5 d orbital and the ligand, what happens to the ligands? The ligands forms a spherical field of negative charge around the metal. So because of these two oppositively charged sphere, the field of two opposite charge fields arises so that the energies of all the 5 d orbitals increases due to the repulsion between the electrons of the metal and the ligands. Okay, so the metal has electrons, no? The electrons of the metal and the ligands already have lone pair electrons. So these two negative charge spheres gets repulsion. Okay, they repel each other and because of this repulsion, what happens? The energy of the 5 d orbital is increases, right? Then the ligands are approaching the metal atom in actual bond direction. Even though the repulsion is existed, the ligands are not stationary, they are moving towards the metal ion along the actual bond direction. The metal bond direction means along minus x-axis plus x-axis plus y-axis minus y-axis plus z-axis minus z-axis. The metal is located at the center of the complex. The ligands are approaching towards x-axis minus x-axis, y-axis minus y-axis, z-axis and minus z-axis. So the orbitals lying along the axis. What are the orbitals lying along the axis? Dx square y square and dz square. These two orbitals will experience a strong repulsion, and the energy gets increases and it is raised. Then the remaining three d orbitals which is placed in between the axis, that is dxy, the orbitals like dxy, dyz and dzx. These three degenerated orbitals has less energy. Now the d orbitals which are lying along the axis and the d orbitals which are lying in between the axis is splitted into two sets of orbitals. This process is called as what? Crystal field splitting. Up to this point, the complex formation would not be favored. However, when the ligands approach further, there will be an attraction between the negatively charged electrons and the positively charged metal ions that result in a net decrease in energy. This decrease in energy is the driving force for the complex formation. See this, we know the geometry of the complexes. The complexes have coordination number 6 means that is octahedral. If the complexes if the complex coordination number is 4 means it is tetrahedral, square planar. If the complex having the coordination number 5 means they are trigonal, bipyramidal and square pyramidal. Okay, now the pattern of splitting d orbital would be depend upon number of ligands, their arrangement around the central metal atom or ion. The pattern of splitting depends upon number of ligands, their arrangement around the central metal atom or ion. Two degenerated d orbitals which is lying along the axis, that is dx square y square and dz square, is the energy of these d orbitals are increases, and these two orbitals are grouped as Eg set of orbitals. The remaining three d orbitals, that is dxy, dyz and dzx. These three orbitals are lying in between the axes. So these three orbitals are called as what? T2g orbitals. During crystal field splitting in octahedral field, in order to maintain the average energy of the orbital, that is Barry center is nothing but the straight line which is drawn in between these two Eg set and T2G level orbital is called as what? Barry center. So the Barry center energy is constant. The average energy is constant. Okay. The energies of the orbitals dx square y square and dz square, that is represented as Eg orbital, will be increased by 3 by 5 octahedral geometry, while the other three orbitals dxy, dyz and dzx, the orbital represented as T2G orbital, decreases by 2 by 5 octahedral geometry. Delta O means what? Octahedral geometry. Here delta O represented the crystal field splitting energy in the octahedral field. The magnitude of crystal field splitting depends upon field strength of the ligand. The first point, field strength of the ligand and charge on the metal ion. If weak field ligands are found means the crystal field splitting is less. If strong field ligands are found means the magnitude of the crystal field splitting will be more. Application of crystal field theory to octahedral complexes. The first one is spectrochemical series. Delta O. The subscript O indicates octahedral geometry. Due to crystal field splitting, the energy of Eg orbital will increase by 3 by 5 delta O, while that of T2G orbital will decrease by 2/5 of delta O. The magnitude of crystal field splitting depends upon the field strength of the ligand and the charge on the metal ion. In weak field ligand, only small degree of crystal field will be experienced, while strong field ligand will cause a greater splitting of orbital. While strong field ligand will cause large splitting of orbital. According to the field strength, the ligands are classified, the ligands are arranged in the decreasing order. See, the order will be iodide has low field strength, bromide, thiocyanide, chloride, sulfide, fluoride, hydroxide, oxalate, water, isothiocyanide, EDTA, amine, ethane 1,2-diamine, cyanide, and carbonyl. Carbonyl has a strong field splitting energy, whereas iodide has a low field splitting energy. Or carbonyl is a strong field ligand, whereas iodide is a weak field ligand. So this series is called as what? Spectrochemical series. Spectrochemical series is derived on the basis of the absorption of light by various chemicals in the presence of light. The absorption of light by various chemical in the presence of light.